Okay guys, so in this video I'm going to take you through the first couple of sections of Chapter 5. We're going to spend all of Chapter 5 in KOM 267. I apologize for canceling class today. This migraine is not going away, so I'm going to try to do this video as quickly as I can so that you'll have a chance to work on some 5.1, 5.2 homework, and then we'll pick up on Tuesday. We'll start with any questions that you have about the first couple of sections, and we'll keep going from there. So just so you know, do watch the whole video, take notes, stop it, rewind it, whatever you need to do, because you are going to be responsible for this information, even if you didn't watch the video. So that's going to be a problem. So you want to make sure that you don't take it lightly. So anyway, the first couple of sections of 5.1, 5.2 are about two variable linear programming. So linear programming problems are problems where you take a lot of parameters. Like here's this situation, for example, on this first page, the Happy Cone Company wants to make two different types of ice cream cones, cake cones and sugar cones, both of which they have to process in the mixing department and the baking department. Manufacturing a batch of cake cones requires an hour in the mixing department, 2 hours in the baking department. Producing a batch of sugar cones requires 2 hours in the mixing department and an hour in the baking department. And each department is operated for at most 12 hours a day. So we've got all these constraints, all these parameters. Our goal, produce the ice cream cones, but we have these constraints. We need this such and such time to do that in each of these departments, and we have a maximum of 12 hours in the baking department, 12 hours in the mixing department that we can do that. So then the question becomes, what are some feasible combinations for cone manufacturing? For example, could we produce 3 batches of cake cones and 2 batches of sugar cones in a single day? Could we produce 4 batches of cake cones and 6 batches of sugar cones in a single day? So that kind of becomes our question, like what's possible, right? There's some things that seem obvious, like I don't think we're going to get 10 batches of each, right? Because even 10 batches is going to be, it's 20 hours in one of the 2 departments, which already, exceeds the 12 hours that we're allowed. But there's some other kind of fine tuning that needs to happen here. So what we end up doing is we end up thinking about what are our parameters and organizing them. Well, just like in Chapter 3, probably the easiest way to organize them is to build yourself a table, which I'm doing here. If you're not familiar with building a table in Word, I suggest that you play around with it some. It's going to be useful. You're going to be able to see what I'm clicking on the screen, so that's nice, which is also one of the reasons I want to meet in the computer lab. In this particular problem, we're talking about cake cones and sugar cones, right? And we also have some constraints about the mixing department and the baking department. Now, as you read the problem, it says manufacturing 1 batch of cake cones, right, requires 1 hour in the mixing department, 2 hours in the baking department. All right, well, so that relates right here. So we've got 1 hour in the mixing, 2 hours in the baking. Sugar cones was the opposite. So producing 1 batch of sugar cones is 2 hours in the mixing department, 1 hour in the baking department. So we've got the opposite happening here. And then we know that for both of these, we have to use up to 12 hours. Now, in previous iterations of this stuff, we want to use 12 hours, right? But this at most 12 hours introduces some variability into it. It could be 12 hours, it could also be 11 or 9.5 or 3, right? So there could be less than that. So I'm going to use the equation writer in Word, which I get to by just hitting Alt equals. You can also go insert equation, right? And it will come up with the equation tools. And I'm going to say what we need here is less than or equal to 12 hours. It's going to happen for both of these. I'm just going to copy and paste this down. All right, so the question, so that kind of organizes our information, right? So this is hours available, right? So, but the question was not this information. This just gets us kind of thinking about it. The question was, what are some feasible combinations for cone manufacturing? All right, so let's take this information and let's look at it a different way. Let's take this and let's consider it differently. So I'm going to kill this stuff off. Let's just delete this. Making a table is really easy. I just hate doing it over and over again. So I'm going to split these into 2 columns and call this cake versus sugar. And we wanted to know, right, like, so could we do, what was it, 3 batches of cake and 2 batches of sugar? Or could we do 4 of cake, 6 of sugar, right? What's possible? Got the mixing department, the baking department. And so if we do this, we can look back and we can say, okay, if we need 3 batches of cake cones, then that's going to be an hour in the mixing, 2 hours in the baking, right? So we've got 3 times 1 over here, and we've got 3 times 2 over here. But we also have 2 batches of sugar cones, which is going to be 2 in the mixing, 1 in the baking, right? So we have to add to that, we have to add to that 2 times 2 and 2 times 1 in the baking. So that means that we've got, what is that, 4, 5, 6, 7 hours in the mixing department and 6, 7, 8 hours in the baking department. So far, this works, right? Let's add a little column over here to the right. Is it feasible? In this particular case, yes, we can do that, right? Because we didn't exceed 12 hours in either one of these departments. Over here, same kind of thing happens, only now we need 4 batches times that 1, 6 batches times that 2, right? So already we're exceeding our limitations because we've got 12 plus 4, which is 16 hours, which is not going to work, right? We can double check that over here, but we already know it can't work. So 4 times 2 and, nope, that's not right. Yeah, 4 times 2 and 6 times 1, right? And so the same thing is going to happen. We've got 8 and 6, and that makes 14 hours, which again exceeds. So no, this is not feasible. We could try other combinations, right? We could say, well, what if we did 5 batches of cake cones and a single batch of sugar cones, right? So could we do it that way? Okay, well, let's look and see what happens. So 5 times 1 plus 1 times 2. Okay, well, that's 7 hours. That'll work. We've got 5 times 2 and 1 times 1. Okay, so that's 11 hours. So that's just under the wire. That also works, right? So that's no problem. So the only one we've found that doesn't work so far is this guy here, right? That one's the one that doesn't work. So the question is, do we want to just keep doing this, right? Do we want to just like keep trying random groupings of cake and sugar cones? I guess we could go about it more systematically, right? Like 2 and 1, 2 and 2, 2 and 3, 2 and 4, etc. But still, that's going to take a long time to negate all of the possible ones, right? So instead, what I'd rather do is look at this in a graph, right? I'd like to be able to take this information and look at it in a graph. In order to do that, I got to know what the graph is supposed to look like. I got to have some things to graph, right? So to graph these ideas, I need to assign some variables, right? So perhaps I say that X is the number of batches of cake cones produced, and Y is the number of batches of sugar cones produced, right? That works. That's no problem. We could have called them A and B. We could have called them Y and X instead of X and Y. So it doesn't really matter. It's very arbitrary. Because remember, at this stage of the game, all we're doing is taking a real context and representing it mathematically so that we can go and solve and then take it back into context. So this is the part where we're just representing this mathematically. So that gives us this system of inequalities, right? I know that 1x and 2y is going to have to be less than or equal to 12, right, due to the mixing constraint, and that 2x plus y is going to be less than or equal to 12 due to the baking constraint, right? No problem. So I've got those two inequalities, and I'm going to put those in Desmos. Now I'm going to try to switch over to Desmos right now. It may knock me off, so I may have to do some video fiddling. We'll see what happens, right? We'll see if it's still talking to me. Go to Desmos. You're probably not seeing this. You may not even be hearing this. I'm going to keep up a little pattern just in case you are. Less than or equal to 12. 2x plus y less than or equal to 12. There it is, right? I also know that x has to be greater than or equal to 0, and so does y, because it doesn't make any sense for us to have a negative number of batches, right? So these points here are going to surround what seems like a feasible region, and of course I just deleted them, which was dumb. Let's try that again. Use my snipping tool to bring this over. And I am still recording, so you may have heard all that, you may not have. That may have just been dead air. If it was, I'll listen to it and give you different directions. But I'm going to kill off the manual graph I put in here and just copy and paste this Desmos graph. Let's just see what happens. So the Desmos graph gives us a pretty clear indication of what's going on. Now in Desmos, sometimes it's hard because Desmos just chooses the colors for you to know what it is we want to really use here. So I'm going to make myself a little color region on top of it. I probably should have told you how I did that. I went to Insert, and then I went to Shapes, and I used the Freeform tool. Now I have this blue, this pretty blue box. The blue, that's a quadrilateral. Blue quadrilateral represents the feasible region. And that's a phrase that you're going to hear a lot. The region that contains all the possible combinations of sugar, well, we'll say cake since it's X, cake and sugar cones that meet all the requirements, right? All the constraints. So there it is. Let's see if we can highlight this blue. That's not what I meant to do. Oh, that's close enough, right? We'll use that blue. That's fine. So there we go. So that's the feasible region. So what that means is all of these points in here that are in this blue quadrilateral, those are the ones that are possible. So now we've contained it, right? We know that if I tried to make 7 batches of one and 2 batches of the other, right, that's going to fall out here outside that feasible region. So that's not going to work. But if I tried to do like 2 of one and 5 of the other, right, that's going to fall in here and that would work just fine. So now we know what it is. Now, a lot of times we get constraints that constrain us even more. So for example, if I know that in the past I've had a steady demand for 4 batches of sugar cones and 2 batches of cake cones, I can use that information to my advantage, right? So for example, at least 4 batches of sugar cones, well, that implies that y, which was our sugar cones, has to be greater than or equal to 4, right? So that's different than what we had before. It also means that at least 2 batches of cake cones, all right, well, that's going to imply that, yeah, that'll work, that our cake cones, right, x, has to be greater than or equal to 2, right? So that's going to work out really well for us. And it changes our graph just a little bit. So I'm going to go back over here and I'm going to change my graph for 2. And it's going to change the feasible region to this very small piece. So instead of the region above, I'm going to end up with this little bitty region here. I'm going to shrink this down so that I don't end up with quite so much work here. Okay, in fact, let's crop this. It's a fun tool. We use the cropping tool. We can come in a little bit. There we go. That's nice. And so that means, again, insert, shapes, freeform. You just click and release. Click and release. Click and release. Click and release. And then once you come back around to your first point, it's going to give you that quadrilateral. So there's our new feasible region. And what's interesting about this is that it has just reduced the number of points I want to try pretty dramatically. So I'm going to say I want to do this. Put it over here with its little yellow box on top of it. Let's bring that back to the front. Or not. There we go. Okay. And so this new feasible region has just 4 feasible points. And so that's going to be 2, 4, and 4, 4, and 2, 5, which we can see as the corners, right? But also, we have 3, 4. Now, the point 3, 4 is inside this region. It's along the border on the bottom in between 2, 4 and 4, 4. The reason I know it'll work is because it's whole numbers, right? So you wouldn't want partial batches, right? Like a 3 1/2, but 4 1/4, that kind of thing. That doesn't work. The way that people manufacture things is they establish what's the most efficient batch size, and that's what they use. And at that point, it becomes just as economical to make a batch of that's a full size than it is to make one that's partial. So you wouldn't make a partial one anyway. So that kind of brings us down to the feasible region, right? Now, so far, so what, right? So what are we trying to do with this? Which one of these combinations would be the best one to use? Well, that depends on a lot of things, right? Maybe it depends on your labor costs in the baking and mixing departments. Maybe it depends on the amount of materials you need to make cake or sugar cones. Maybe it depends upon the profit that you bring in based on cake and sugar cones. And in fact, we're going to look at a scenario where the revenue is what we know. Suppose a batch of sugar cones sells for $535 and a batch of cake cones for $419. So we know how much money is coming in. What combination of cone manufacturing would make the revenue for this company maximized? How would it maximize it? So if we want to maximize the revenue, we need to come up with some kind of formula for the revenue, right? We could take each of these points back here and we could plug them in and say, 2 times 419 plus 4 times 535, right? We could do that and we could figure out what's going on. So at this point, we've gotten to a system that looks like this. Now, we don't need to write this out to solve this problem, but being able to write this out on a regular basis is going to be really helpful later in the chapter, so I'm just going to go ahead and do it. All right, so if I want to maximize revenue, what I'm really trying to maximize is 535 times y, that's 25, 35 times y, plus 419 times x, right? Subject to all of those constraints that I just brought up, right? So those constraints were, I had 2x plus y less than or equal to 12. I had x plus 2y less than or equal to 12. I had x greater than or equal to 2, and I had y greater than or equal to 4, right? No big deal. So this is what's known as a linear system, this guy right here. This is really handy, and it helps us to keep things in line. I encourage you to, on a regular basis, go ahead and write out your linear programming system. It's going to be useful. All right. Now we could try all 4 of those points. And with just 4 points, it's really not hard to do. But there's another piece of information that we have here that's going to help us to establish the best way to go about this. So, and I don't think this is oriented properly. Yeah, let's go around and to the right. There we go. All right. So we're going to talk about the corner point theorem. The corner point theorem tells us that the optimal solution will always be one of the corner points of the feasible region. So that means that even way up here when we were looking at this big area, we know that the maximized option is going to be either 0, 0, 0, 6, 4, 4, or 6, 0. So down here in our little region, we've got these 3 points, 2, 5, 2, 4, and 4, 4, that we can try. What that means is we can take each of those, 2, 4, 4, 4, and 2, 5, and we can try them out in this this maximization, right? So if we take this and we put them in, we can say, okay, so times 2, right? Times 4, times 4, times 4, and prove this to yourself, right? Like, it's really easy. Oh, I did those wrong because this was y, wasn't it? This is 4 and this is 2. Pardon me. Prove this to yourself. Don't take my word for it, right? Pause the video. See if you can get these calculations to come out the same way that I do. Anytime you're doing math from a video or a book or whatever, it's a good idea to go back and double check yourself and make sure that you know how those numbers came about, right? Don't just go trusting everything that you see. So if I do these calculations, I end up with this revenue. For 2 batches of cake cones, 4 batches of sugar cones, I end up with $27.46. For 4 batches each, I get $38.16. Oops. And for 2 batches of cake, 5 batches of sugar, I get $35.13. So, so clearly the winner, right, is this guy here. Right, there's our clear winner. And so we know we can optimize by making 4 batches of each. Because this problem comes with constraints, though, it's not enough to simply state the maximum revenue and the corner point that revealed it. Instead, we need to attend to all parts of the problem context, which means what's the maximum revenue? What production provided it, right? And did we use up all the available hours to do so? Now, that seems silly. I know it seems a little pedantic to say, no, you have to go and figure out what happened in the baking and mixing departments. But when you think about it, like if you're running a company, you need to know that, right? That affects your labor costs. It affects benefits that you're paying out. It affects how you hire, right? All those kinds of things. It also affects, like, how do you care for your employees? Are they getting the hours that they need to make a living? All that kind of thing. Sometimes the most efficient way is not the most caring way. But anyway, that's just me. It's a tree hugger in me. What are you going to do? All right. So what I find out is this. If I was to take this information right here, this maximized revenue thing, let's plant it down here and let's re-examine it. I'm going to add a column to the right, or yeah, to the right over here. And I'm going to say, so what happened, right? What was the result for 4, 4? We decided that was the optimal solution. So we end up with a revenue of $38.16. We already know that. We also know that if we take 2 times 4 plus 4, we're going to end up with exactly 12, right? 8 plus 4 is 12. So 12 hours are going to be used in both the baking and mixing departments. So the full solution here is that the company should make 4 batches each of cake and sugar cones. Doing so, they will use up, they will make $3,816 in revenue and use all 12 hours available in both the mixing and baking departments. Okay, and that is a complete answer, which is going to feel a little annoying right now, but I promise you in the long run it's going to be really useful to you. As you do your homework for this chapter, you're going to want to be that complete with all of this. You're going to want to make sure that you're always looking for the most complete answer, even if they don't ask you for it. Go ahead and find what all the parameters are doing. So if we go all the way back up here to our organizational scheme, we should be accounting for the number of batches of cake cones, the number of batches of sugar cones, and what's happening in the mixing and baking departments. All right, so I'm going to leave it there. You have the tools that you need right now to look at sections 5.1 and 5.2 in your homework. And when I see you on next Tuesday, I will start by asking you to give me your questions, and we'll talk about those, and then we'll continue on into 5.3 and 5.4. So have a good weekend. Thank you for your patience, and I hope we all feel better. In particular, me right now. Okay, bye.